My name is Ruby Standmeyer. I work in the drinking water program at EPA Region 3, and I'm going to kick us off today with our session on PFAS. So just a brief overview on some of the topics we will cover today are some updates on EPA's PFAS strategic roadmap, a bit of background on what PFAS is and why we're talking about it today, EPA's approach and some of our goals and actions on water specifically, the bipartisan infrastructure law and funding for PFAS, and then we'll end today talking about water quality criteria and Pennsylvania's updates on PFAS, which I will turn over to some of my colleagues for. But for now, next slide, please. Great. Okay, so our administrator, Michael Regan, here at EPA, has started his tenure extremely focused on PFAS. So that's been a big priority of his and now of EPA as well. So back in April 2021, he established the EPA Council on PFAS. And one of their first goals that they had to accomplish was to create a roadmap on PFAS strategy at the agency. So the PFAS roadmap is a whole of EPA strategy, and that means it uses all of our different regulatory authorities and uses all the different program areas within EPA to protect public health and the environment from PFAS. So it outlines actions in water, air, Superfund, soil, pretty much anything you can think of that EPA does. We try to address that in the roadmap. And it also sets timelines and deadlines for specific actions. And those actions started in 2021 and will take us through 2024 and beyond. And then the diagram on the left does, it's one of my favorite PFAS diagrams. I think it does a great job at showing the different pathways by which PFAS can enter the environment, anywhere from the actual manufacturing sites where PFAS is being manufactured to the application of biosolids on agricultural lands, the use of film, firefighting foam that often results in PFAS hotspots around either domestic, civilian, or military airports or Air Force bases. And then, of course, landfills, wastewater treatment plants, and PFAS can enter drinking water systems and private wells. Next slide, please. Okay, so when I see the term PFAS, that is short for per and polyfluoroalkyl substances, which is a mouthful. So that's why everybody pretty much just refers to it as PFAS. And PFAS is an umbrella term that covers thousands of different chemicals under that category of PFAS. So they are man-made synthetic chemicals, and they're all unique, but all similar. I won't get into the chemistry of it, but the main characteristic of a PFAS chemical is chains of carbon atoms that are surrounded by fluorine atoms. But besides that, there's a really wide variety of what their chemical structures actually look like. PFAS have been used in homes, businesses, and industry since the 1940s. You can find them in soil samples, water, air samples, and most people today have been exposed to various levels of PFAS. And the reason why this is concerning is because there are known or suspected toxicity effects due to PFAS. This can result in potential developmental, liver, immune, and thyroid effects. Some of these effects are pretty well understood, many are not. And then part of what makes PFAS so useful in industry and in consumer products is that they don't decompose. And that's why we call them forever chemicals. So they really resist decomposition. However, the flip side is that this is what makes it so dangerous in the environment and in the human body, because once it's there, it's there to stay. Next slide, please. Okay, so I'm sure today you've heard a lot about the bipartisan infrastructure law, which is a huge investment in water infrastructure. And one of the large priorities under what we call BILL, bipartisan infrastructure law, is to focus on PFAS. So BILL is providing a total of $10 billion to invest in communities that are impacted by PFAS and other emerging contaminants, but specifically focusing on PFAS. And there's three main areas or pots of funding where that money is going to be allocated through. So firstly, $4 billion will be allocated through the Drinking Water State Revolving Fund, and then $1 billion will be allocated through the Clean Water State Revolving Fund. Then there's a $5 billion that is going to be given to a new grant program that is the Small or Disadvantaged Communities Drinking Water Grants. And this funding will be for communities that, like the title said, are either small or disadvantaged. Back in February, EPA announced the first round of allotments under this grant program. And in total for this first round, EPA will award $178.5 million to Region 3 grantees. And in Region 3, that includes the District of Columbia, Delaware, Maryland, Pennsylvania, Virginia, and West Virginia. There is guidance available online, and you can find out the more specifics on the allotment amounts that each state and each grantee is getting on EPA's website. And our states and DC are currently working on their work plans for this first round of funding. Next slide, please. And then just to look in a little bit more specifically on the SRF, the State Revolving Fund, the bipartisan infrastructure law created 5 new separate pots of funding, and 3 of these are in the Drinking Water State Revolving Fund, and 2 of them are in the Clean Water State Revolving Fund. And I've highlighted the emerging contaminants kind of buckets of money. So you can see that's a pretty substantial amount of money that will be coming through the DWSRF and through the Clean Water SRF. However, the general supplemental buckets of money, those can also be used for projects that are related for PFAS. However, the emerging contaminants pots of funding can only be used for PFAS and other emerging contaminants. So all this to say is that there's a lot of funding opportunities right now. There's a lot of opportunity for states and local systems to access this historic amount of funding. Next slide, please. So some of the actions that we have to protect our water, and hopefully the funding that we are providing will help states and systems with accomplishing these goals and these actions. Firstly, EPA is setting enforceable limits for PFOA and PFOS in drinking water, and we recently announced our proposed rule earlier this year that I will discuss on our next slide. EPA is also working to improve PFAS drinking water data through monitoring, toxicity assessments, and health advisories. EPA is developing technology-based PFAS limits for industrial dischargers, and is also addressing PFAS in Clean Water Act permitting, developing new and improved analytical methods, water quality criteria, and fish advisories. And then lastly, I think this is a pretty hot topic right now. EPA is working on evaluating risks of PFAS in biosolids and working on a guidance document for that. Next slide. So this goes into our current proposed rule for the PFAS National Primary Drinking Water Regulation, the NPDWR. So EPA is proposing to regulate PFOA and PFOS separately as individual chemicals, and the proposed maximum contaminant level is 4 parts per trillion for each, for PFOA and for PFOS. Additionally, EPA is proposing to regulate 4 other chemicals, PFNA, PFHXS, PFBS, and what we call Gen X chemicals. And the proposal would regulate those as under a hazard index, which is a unitless tool that we can use to evaluate potential health risks from exposure to chemical mixtures. So those 4 would be regulated as a mixture of chemicals. The proposed maximum contaminant level goal is set at, or would be set at 0 parts per trillion for both PFOA and PFOS. EPA is currently gathering public comments. So the public comment period is currently open through May 30th, 2023. So if anybody has comments, questions, concerns on this proposed rule, I urge you to go online and find the public docket where you can submit your public comment. And these will all be taken into consideration as EPA prepares to work on our final rule for this. There was a public hearing on May 4th where members of the public were able to provide verbal comments on the rule proposal as well. And if you have any trouble with finding the public docket or want more information, please don't hesitate to reach out to me or anyone in the region. Next slide. So a little bit more on what this proposed rule is actually going to do. So this proposal would require public water systems to monitor for all of these PFAS, to notify the public of the level of these PFAS. And then if the results exceed the proposed standards, they'd have to work to reduce the levels of those PFAS, whether by installing new treatment or identifying new sources of drinking water. Again, EPA is requesting comment on this proposed rule, and we're specifically requesting comment on our preliminary determination to regulate those 4 additional chemicals as a mixture and as a hazard index. This action is not final. Again, it is a proposal and it does not require any actions until after EPA has considered all public input, all public comment, and until we finalize the regulation. And we hope to finalize and publish the final rule by the end of 2023. And this got a little bit cut off, that final bullet point, but EPA does anticipate that if fully implemented, this rule will prevent tens of thousands of illnesses and PFAS-related deaths. Next slide. All right, so moving on to a different rule, we have the Unregulated Contaminant Monitoring Rule, which is under the Safe Drinking Water Act, is a rule designed to collect data and information on contaminants that are not yet federally regulated. So we are currently in the 5th cycle of the UCMR, what we call UCMR 5. And UCMR 5 is sampling and monitoring for 29 different PFAS chemicals. This is a pretty huge increase from previous UCMR. The last UCMR cycle that analyzed for PFAS was UCMR 3, and I believe that only included 6 PFAS chemicals. So this is really going to expand the amount of data and information we have on 29 different PFAS chemicals. Sampling has started in January of this year, 2023, and will continue throughout December of 2025. All public water systems that serve 3,300 or more people will collect samples, as well as a representative number of small public water systems that serve less than 3,300. For these small systems, EPA will be the one to arrange for the analysis of those samples and will pay for the shipping and analytical costs to try and offset the burden, since it's not cheap to analyze and sample for PFAS. And this effort especially will expand the number of water systems that participate in sampling. So under UCMR 5, more systems will be sampling for all of these PFAS. So again, not only will we get more information on more PFAS, but we'll also get data from more water systems than previously. So this will be, once we have all the data, this will be pretty huge for our data efforts. So that is a very quick snapshot of some of the things happening in the drinking water world. And without further ado, I'd like to hand it over to my colleague, Charlie Brown, who will be talking about water quality criteria.
Thanks, Ruby. So yes, my name is Charlie Brown, and today I'm going to talk to you about the development of the PFOA and PFOS criteria to protect aquatic life. Next slide, please. So real quick, I want to take some time to talk about water quality criteria in preparation for the next few slides. Generally speaking, EPA develops criteria for determining when surface water has become unsafe for people and wildlife using the latest scientific knowledge. And it is under Section 304A1 of the Clean Water Act that directs EPA to develop these criteria. More specifically, tribes and states use EPA-recommended water quality criteria for aquatic life to develop water quality standards in order to protect and restore waters, issue permits to control discharges, and assess the cumulative impact of pollution on local communities. Next slide, please. Aquatic life criteria defines how much of a chemical can be present in surface water, whether it happens to be fresh or salt water, before it's likely to harm plant or animal life. These criteria are designed to be protective of 95% of tested aquatic organisms representing the aquatic community. 3 components are considered when determining aquatic life criteria: the magnitude, or the exposure, concentration of exposure, the duration, or the length of time an organism is exposed to an average concentration, and the frequency of exposures. Acute criteria is defined as the highest concentration at which the aquatic community can be briefly exposed without an adverse effect, while chronic criteria is defined as the highest concentration at which the aquatic community can be indefinitely exposed without adverse effect. Next slide, please. Starting with the top of the slide and moving down, I'll briefly go over the process of criteria development. So effects data used for criteria are selected from experiments performed on or and directly impact the most sensitive life stages of an organism. These data are derived from published manuscripts that have been peer-reviewed by the scientific community. While the resulting criteria will be applicable to all life stages, ranging from the least sensitive stages like adults to the most sensitive life stages such as embryos, by deriving criteria based on the toxicity data for the most sensitive life stages, the criteria is thus designed to be protective of the entire life cycle of the aquatic organisms. Acceptable acute data can be in the forms of LC50 or EC50. While the concentration of a pollutant that elicits a 50% mortality of a group of organisms is pretty straightforward, such as an LC50, the effects concentration, or EC50, may be in the form of something like deformities. While a deformity may not outright be lethal, a deformed organism can be expected to be not as fit as it would normally be, which may possibly reduce their ability to capture prey or escape predation. While data quality requirements are the same for deriving both acute and chronic criteria, because it's more difficult to obtain sufficiently adequate chronic data due to the time and expenses associated with those studies, the acute to chronic ratio can be used to derive chronic values from acute values. The ACR value, or acute to chronic ratio, is created by using ratios derived from studies in which both acute and chronic tests have been conducted simultaneously for the same species. In short, through the use of additional calculations, the final acute and chronic values are calculated, which are then used to calculate criteria. Next slide, please. When developing protective aquatic life criteria, EPA regulations require toxicity data from a taxonomically diverse set of animals, which includes multiple chordates, such as fish and amphibians, in addition to inverts, such as planktonic and benthic crustaceans, insects, rotifers, annelids, or mollusks. These taxonomic requirements are referred to as the minimum data requirements, or MDRs. And they ensure that animals from multiple niches within the aquatic community are considered in criteria development. When selecting source data, additional experimental condition requirements need to be met, as well as that ensure proper experimental design. So as you can see, for data to be acceptable for criteria derivation, a lot of checkboxes must be marked. This ensures that the aquatic community, and not just a few organisms, is protected, and that the data selected for criteria development is accurate. Next slide, please. In developing criteria, it's also important to consider how PFOA and PFOS behave in the environment, as the fate and transport of those pollutants can influence how organisms are exposed, and once exposed, what are the target tissues of those pollutants. For instance, PFOA and PFOS are known to be resistant to biodegradation and are environmentally persistent. They're difficult for organisms to eliminate from the body, where they are typically eliminated via the body, but then reabsorbed into the intestines and back into the body. And they are proteinophilic, binding to proteins in blood, muscle, kidney, and the liver. These properties also influence how an organism can be exposed to environmental PFOA or PFOS. If in the water column, they can bind to blood proteins at the surface of the gills, they tend to absorb to sediments and biofilms, impacting benthic or bottom-feeding organisms, and they bind to yolk proteins like albumin or vitellogenin, making maternal transfer of PFOA and PFOS to eggs a route of early life stage exposure. Ultimately, knowing possible routes of exposure to PFOA and PFOS is important in selecting which animals are chosen that represent the aquatic community. However, finding adequate data within the previously mentioned experimental and taxonomic constraints has proven to be very difficult for PFAS. Next slide, please. In this example, effects data was selected from numerous experiments, vetted to ensure the data met the previously mentioned experimental requirements, and then research organisms were ranked in order of sensitivity. The four most sensitive organisms, indicated here in the red box, are then used to calculate the acute criteria. In this example for PFOS, only 7 of the 8 MDRs were met, This is also true for PFOA, as insect data for both was highly variable. Next slide, please. Here's a list of the 4 most sensitive genera taken from the previous figure for PFOS and PFOA, exposure in fresh water. Data is represented as the genus mean acute value, or GMAV. When data is available for multiple species of the same genus, it's taken like that. Otherwise, single species values are used. Ultimately, this data will be used to calculate the acute freshwater criteria for these 2 compounds, with the process repeated similarly for chronic criteria. However, EPA normally uses tox data from North American species only. But when data is sparse, especially for the multiple types of animal phylogenies needed for criteria development of a class of chemicals with a relatively young body of research, non-native species can be used, as indicated by the bold text. These species are selected based on the taxonomic and effects responses relatedness to North American species and could be considered as surrogates. Next slide, please. However, as indicated here in this list of PFOS sensitivities for saltwater animals, sometimes sufficient acceptable data is just not available to complete the 8 MDR requirements. Next slide. Here, even with the use of surrogates, the data available for saltwater species fulfilled only 5 of the 8 taxonomic MDRs for PFOS and 4 of the 8 for PFOA. As a reminder, those taxonomic MDRs are required such that the developed criteria endpoint is sufficiently protective of multiple types of animals in the aquatic community. So developing criteria that's wholly protective of the community is an important goal to try and meet. Next slide, please. For the chronic saltwater criteria, data is even more sparse. For PFOS, 3 of the 8 MDRs was fulfilled, but for PFOA, no quantitatively acceptable data was available for saltwater animals. So, in the interest of providing recommendations to states and authorized tribes on protective values, model-derived endpoints were estimated. Next slide. The new approach methods are a technology, methodology, approach, or combination that can provide information on chemical hazard and risk assessment in lieu of toxicity testing. So, to fill the gaps for the saltwater criteria, EPA developed an estuarine marine criteria benchmark using available empirical data, supplemented with toxicity values that were generated through the use of the new approach methods, specifically through the use of the web-based interspecies correlation estimate, or WebICE. As indicated in this figure, these models are log linear regressions of toxicity responses of 2 species across a wide range of chemicals, thus representing a relationship of inherent sensitivity between those species. So, if the fit statistics are appropriate, then the sensitivity of the modeled organism can be inferred from the surrogate organism. Next, please. Here's a list of parameters used to evaluate model robustness. Specifically, both slopes and R-squared values need to be above 0.6, and the mean squared error, or MSE, needs to be below 0.95. The geometric means of estimated toxicity are then taken from models that pass these criteria, and that geometric mean is incorporated into the ranking of MDRs to derive a criteria value. Next slide, please. To summarize, aquatic life criteria is defined as how much of a chemical can be present in the surface water, whether it happens to be fresh or salt water, before it is likely to harm plant or animal life. These criteria are designed to be protective of 95% of tested aquatic organisms representing the aquatic community, with the chronic criteria designed to protect aquatic life from PFOA and PFOS bioaccumulation. And this is reflected in the calculation for the tissue criteria, which is a product of the chronic criteria times the bioaccumulation factor And that bioaccumulation factor itself is derived from field and laboratory studies. However, data limitations prevented establishment of criteria protective of estuarine and marine waters. However, the new approach method via the interspecies correlation was used to model the acute saltwater values. Thus, these are not criteria, but are currently recommendations that require additional research to confirm. In instances where bioaccumulation has occurred in fish, for example, the consumption of those fish and or the water in which they reside can be an important pathway for PFOA and PFOS exposure in humans. Next slide, please. Human health criteria defines how much of a chemical can be present in those waters before it's likely to impact people when they drink the ambient water or eat aquatic life, such as fish or crawfish, that are in those contaminated water bodies. However, the road to developing human health criteria for PFAS in general is a little bit more difficult for several reasons. Again, PFAS toxicity is a relatively young research field, and EPA wants to utilize the latest science that's still rapidly advancing and evolving to determine what's protective of human health. Additional research needs to go into the interactions of the route of ingestion, such as drinking water or consuming fish, duration of exposure, how much fish is consumed, and the age of the person. And this interaction needs to be studied for individual PFAS as the specifics of those interactions are likely to differ based on the individual PFAS compound. Thus, the difficulty lies in part in the fact that EPA must determine toxicity and bioaccumulation in the animals and the interaction with the people who use those animals for sustenance. This human health criteria for PFOA and PFOS is expected in 2024. And that is it for me. Thank you for listening, and I'll pass on the presentation to Amy.
Hello, you can switch to the other slide. Okay. My apologies, my video isn't working. I've tried, but apparently it's a black screen. I may be blocked with the Zoom or something. I'm going to talk to you a bit about the Pennsylvania DEP surface water PFAS monitoring. So the field work we're doing for PFAS for the past several years, since 2019. So you can switch slides. So a lot of people before me have already talked about the introduction of PFAS, so I'm not really going to go into a lot of details with it. They did a good job. Obviously, PFAS are man-made chemicals. They're persistent and don't break down easily in both the environment and the human body. There are thousands of different PFAS chemicals, but we only test for a subset. And the tree here, I like that gives examples of the different groups, like the perfluoroalkyls and polyfluoroalkyls. So PFAS were produced a lot in the US and are commonly found in the environment now. They've been phased out of production and replaced by other chemicals, but we're still seeing them a lot. Next slide. As also described before, they're in a lot of different uses: firefighting foams, detergents, paint, food packaging, nonstick coatings. They have stain, water, and grease resistance, and metal plating. They're in pesticides, photography, to just, the list goes on and on. Next slide. And of course, we are now finding that we can get exposed to PFAS through drinking water, fish, meat, paper products, dust, consumer products, through placenta, breast milk, and food, of course. Next slide. And also, as described, they're persistent in the human body, can be associated with a variety of different ailments. I have a little ill liver there. So apparently it can cause liver damage and also problems with development and reproductive systems. Next slide. So environmentally, they are very persistent and they don't break down. They've been detected, of course, in public water systems, and the extreme areas of concentration include the AFFF sites, industrial areas, landfills, and wastewater treatment. Okay, next slide. So Pennsylvania largely became involved in sampling through that third unregulated contaminant monitoring rule that was described before. And the first thing that occurred was about 175 out of 3,000 public water systems were sampled in Pennsylvania. And since then, PFAS sampling has occurred regularly at different Pennsylvania public water systems. And we also started collecting at surface water to see what the issues are there. The initial effort started in 2019 and targeted 178 Pennsylvania Water Quality Network, or WQN stations. And we collected a single data collection event at each. This WQN is a statewide fixed water quality sampling system that was established to characterize water quality conditions across Pennsylvania's surface waters and across the country too. And it's there are lots of other compounds that are tested for at these sites. So they're chosen for a variety of different reasons. So it made a good sample size to start sampling across the state for a general survey. Samples from all of these stations were analyzed for 33 PFAS chemicals and 19 top chemicals, total oxidizable precursors. A top assay will treat the samples to potentially expose PFAS chemicals that can transform into terminal PFAS compounds. And it can provide the opportunity to understand if other PFAS compounds are present that we aren't specifically testing for. So it's kind of a novel concept when we first started doing it, at least to me, but it's very informative. The samples were analyzed at SGS Access Analytical Services in British Columbia, Canada. And prior to collection, so DEP staff, USGS, and SRBC, Susquehanna River Basin Commission staff, collected these samples. We conducted rigorous quality assurance testing to ensure that the equipment and protocols being used would not contaminate the samples. So there's a whole other data set on that. So we feel pretty confident that the methodologies we're using was not contributing to any detections. In addition, we also deployed passive water samplers, which I'll describe later, at 18 sites across Pennsylvania at that same time. Next slide. So you probably can't see this very well. I can post it in the chat if we need it later. But this is the location on the DEP website where that links to the results from that 2019 sampling. The USGS PFAS data 2019 link will take you to the USGS site where they have a publication of just all the data from that study. And then the surface water PFAS summary 2019 is a HTML document that has interactive maps where you can click on dots to see the results. And I'll show a couple of those maps, not interacting with them, but screenshots in a little bit here. The highest PFAS and plus PFOA water concentrations that we found were in southeastern PA, which weren't surprising because this is near the Air Force Base, was at Neshaminy Creek, Valley Creek, which is near Valley Forge, and Wissahickon Creek. So they're all near the Philadelphia area. So subsequent to that collection effort, and based on results that we found, we collected additional data in 2020 through 2022, and it's ongoing at WQN sites that had the higher concentrations and were areas of concern at fewer locations than this 178 site study. And we also started collecting fish tissue data at sites as well. And since then, I'm going to talk about this a little later too, there was a fish consumption advisory placed on the Neshaminy Creek watershed based on the fish tissue results. Next slide. So Again, this is kind of a busy slide, but that HTML document I told you about does show this same table. These are all the compounds that we analyzed for, and a little X is next to the ones that we did that top analysis for. Next slide. So as I mentioned, we also deployed passive water samplers. Those were POSIS, Polar Organic Chemical Integrated Samplers, that we used to test for PFAS. They are comprised of microporous polyether sulfone membranes with a solid phase sorbent that in the middle that samples hydrophilic contaminants. They're placed in the field for about a month. We did approximately 30 days. And they're capable of detecting very low level contamination or contamination that occurs infrequently, sporadically, that may not be detected in discrete surface water samples. And we found this technology to be very useful in sampling for emerging contaminants or other contaminants that would have a biological effect at extremely low concentrations. Next slide. This is a photo of the POSIS. So there is actually, that's one holder with 3 membranes. So we typically, I think for the PFOS samples, I believe it is 3 of those membrane or 4 of those membranes that is used to, is combined after it's extracted at our contract laboratory, which is EST Labs in Missouri. They will extract and condense into an ampule the compound of the what results from these membranes. And I think 4 of those are combined and then sent over to the laboratory, in this case, the British Columbia Axis Lab for analysis. So after we get those results, we get them in nanogram per POSIS. So it's kind of a unitless result. You can use that alone. You could sort them from low concentration to high concentration to see what sites were highly contaminated or not very contaminated. But we can also, with some compounds, convert using sampling, a lab-derived sampling rate to convert to nanogram per liter or whatever unit you choose to. And that's called a time-weighted average, or TWA calculation. So it's a little bit involved. We do our own calculations now. When we first started doing sampling with passive samplers about, I guess it was over 10 years ago now, USGS, who helped develop this, did the calculations, but it's moved over to our jurisdiction now. Next slide. So just some photos here for the passive samplers. That's right after deployment. You can see they're in stainless steel canisters. They're kind of bright. We normally, this is for to show you guys before we put some rocks over them, but we normally try to hide these a bit. We don't paint them or anything. We try to avoid any other organic contamination on these. So they are not very well hidden all the time, but we do tend to kind of shade them with rocks. You also don't want them to be directly exposed to sunlight during the duration of deployment if possible. Next slide. And then when we get them out, the canisters are often covered with algae, as you can see here. We get them out, put them in those tins directly from the canister into the tins, and don't expose them to the air. POSIS aren't as good air samplers, but other passive samplers that we use called SPMDs are effective air samplers. So we try to avoid exposure to the air as much as possible. Yeah. Next slide. this is one of the maps that is in the HTML document. If you decide to look online at it, it's an interactive map. It looks very busy, but what you do is you can toggle the different items in the legend on and off. So right now I have the PFOS grabs from that 2019 sampling, and this is summed. So we summed the total of the PFBS, PFOS, PFOA, PFHXA, PFNA, PFDA, and PFDOA in those samples to obtain those concentrations. And the reason we used those compounds is because those were the ones that we were able to take the raw passive sampler results at any of the sites that overlapped and convert to the time-weighted average. So that's a caveat with this, but those are also listed in the HTML document. So if that top result that I described was higher than the original PFOS result in the grab sample, the top value was actually used. So this is kind of showing what could also occur at the site. As I mentioned before, the highest samples were at the Neshaminy Creek, Valley Creek, and Wissahickon Creek. The highest total PFOS total weighted average concentration from the passive samples was also at Neshaminy Creek. So that was 242 nanogram per liter at Neshaminy Creek, whereas the actual grab sample concentration was significantly lower. You can see on the legend there at Neshaminy Creek. So the passive samplers definitely concentrate the results. Next slide. Okay, this is a map of the same sites, but instead of concentrations, this is total number of detections. These are the grab samples. Although if you toggled off that grab and clicked on the POSIS, you would just see the POSIS sites. You can see there's slightly different legends for those. So again, if the top analysis resulted in a discrete sample detection, while the initial analysis did not, the top result was counted. So while the sites with the highest total PFOS and PFOS or PFOA concentrations did have the highest number of PFOS chemicals, one thing that's worth noting is many sites with very low level of detections had a high number of compounds detected. So for example, around Harrisburg, where I am, Paxton Creek, had lower concentrations, but a large number of different PFOS compounds detected. And this pattern was observed in both the grab samples and the POSIS samples. The highest number of PFOS detections in the grab samples was 10, which occurred at several sites, including Neshaminy Creek and Valley Creek and Wissahickon Creek. And the highest number of detections in POSIS samples was 18, occurring actually in the Lehigh River and the Delaware River at Trenton. So those had lower concentrations, but a high quantity of PFOS contaminants detected in the POSIS samples. Next slide. So also for the 2019 results, this is just the total PFOS for the POSIS. So you can see we obviously only did 18 sites. So those are scattered across the state. And we summed those same 7 compounds that I mentioned before here. And of course, the highest concentration was in the Philly region. Next slide. Okay, and for total number of detections, the same thing that I described before. The highest number of detections was 18, occurring in the Lehigh River and the Delaware River. Next slide. So subsequent to that sampling, we along with USGS, developed a list of sites of concern out of those sites. And these are the sites that were sampled from 2020 through 2022. So obviously around the Philadelphia area, and we had a number of sites in the west of Pittsburgh. Next slide. So after doing all the grab samples, we also decided to do passive samples at sites of concern, and also a couple additional reasons. And we have some control sites, reference sites. We also paired grab samples at some of the passive sample sites. So we have comparisons now that include a variety of chemicals, but PFAS at passive and discrete sites from 2019 through 2022 at the sites indicated here. The next map. So briefly, some of the results from the water sampling at the grab samples at water quality network sites from 2020 through 2021 are shown here. So I should note that this sampling occurred approximately monthly. So we're trying to get trend information across sites. And this shows the total PFAS, but this time is the sum of all detected PFAS compounds. So that includes the Gen X compounds, PFBS, PFHPA, PFHXS, PFHXA, PFNA, PFOA, and PFOS. Those were the compounds detected. Highest ones being in the far west, I believe that's Mahoning River actually, and around the Air Force Base in Philadelphia. Next slide. So the last thing I'm going to mention is the fish tissue. As I said, we have been doing a lot more fish tissue analyses for PFAS, and we've issued one do not eat advisory so far. That's in the Neshaminy Creek Basin in Bucks and Montgomery counties due to PFOS. And that extends right now throughout the entire Neshaminy Creek Basin, although I know staff now are sampling more this year to try to narrow down exactly how widespread the problem is. And you can read a little bit about that work at the link that's listed there below. So my closing slide, I just have some, if you have any questions, I have my information. I don't know if you want a bit to copy down that link, if you want to look at the Neshaminy Creek information too. So that's what I've got. Any questions? Or any questions for anyone, I suppose?
Okay, this one's for the group. Given the widespread use and occurrence of PFAS compounds across the country, how is EPA working with other federal agencies, such as the FDA, Commerce Department, Defense Department, or the Consumer Product Safety Commission to remove sources of PFAS and prevent them from entering the environment?
I can go first and answer some of those agencies anyway. I think one of the most close federal partner that EPA has been working with on PFAS has been the Department of Defense. EPA has been working closely with DoD on federal facilities in particular, and a lot of Superfund sites, and as well as on a lot of different research projects. So I think recently EPA and DoD, as well as state partners, have been working together to look for new ways to destroy PFAS in firefighting foam that we learned about previously today. Some of the other ongoing studies and collaborations between the two agencies involve studying the emissions and efficacy of thermal treatment and removal of PFAS from soil, as well as the incineration of spent granular activated carbon, or GAC, and the incineration of spent ion exchange materials. And there was also a study on performance and cost models for groundwater remediation. And I believe DoD has worked closely with EPA on our new and updated and pending laboratory methods. So we have some new lab methods coming that DoD has been working on with us. And then lastly, the National Defense Authorization Act for fiscal year 2020 included a section that added certain PFAS to the list of chemicals that are covered by the Toxics Release Inventory. And that's covered under the Emergency Planning and Community Right to Know Act, and provides a framework for additional PFAS to be added to the TRI on an annual basis. So I know that that is also ongoing and began in fiscal year 2020.
And while I can't speak for any other agencies, I can say that within the EPA, the National Pollution Discharge Elimination System, or NPDES, can be used to restrict PFAS discharges from point sources and help EPA obtain info on the sources and quantify those discharges. Additionally, guidance has been issued to optimize industrial operations, improve industrial housekeeping practices, and help with equipment decontamination or replacement practices.
Thanks, Ruby. Thanks, Charlie. Looks like we have another question here, and it is concerning synthetic playing turf, and if EPA measures PFAS in these synthetic turfs before the PFAS enters the water, or anything else you can comment on this.
I don't think I have any expertise or particular knowledge about synthetic turf. As far as I know, we don't measure PFAS in specific locations of synthetic turf before it enters the water, but that can definitely be a source of it. So I don't have any specialized knowledge.
Thank you. And it looks like Sheldon included their email address too as well. So if anybody has information or would like to speak to Sheldon about that, you can go ahead. All right. We have another one. It says, were the PFAS grab samples taken at the surface water air interface or deeper in the water column, like the POCIS? This might be for Amy.
Yeah, they so they collected these were done, as I said, mainly by USGS, SRBC, and DEP staff. They were collected similarly to other water quality network samples, which is across the it was a composite sample, which is then surface water air interface. It was deeper in the water column, but not at the bottom like the POCIS. Whenever we collected the grab samples along with the POCIS, those were collected according to DEP's normal water sampling at a site, which is mid-column, mid-depth.
Thanks, Amy. Now this one is for Charlie. Will there be saltwater chronic criteria, or is there a reason why they are not derived?
Yes, I would like to think there will be, but currently the draft version of the Aquatic Life Criteria is released, and at the time of the release of the draft, there was insufficient data or insufficient studies out there to derive that. Thus, the new approach method was used. So I think there will be, but yeah, we will see.
Thanks, Charlie. And then the last question I'm seeing here for now is, what do we think this means for the safety of drinking water? I've heard certain water filters can filter PFAS. Do you know of any, or are you aware of any?
Short answer, yes. There's various different types of treatment that can be installed for treating PFAS, some at the utility level, but there's also water filters that are NSF certified to reduce PFAS levels. Currently, they're only certified to reduce to the previous EPA health advisory, which was 70 parts per trillion for PFOA and PFOS. That health advisory was updated last summer to near zero levels. And NSF and private companies are still working on reevaluating and redoing their certification, but those filters can reduce PFAS to safer levels. I think NSF has a pretty good site for sample filters that you can buy, as long as you're making sure that they are NSF certified. And then in terms of the safety of drinking water, I think PFAS can be similar to lead in a way, with our super low health advisories, and with both PFOA and PFOS having an MCLG of 0, that basically means that there really is no safe level of PFAS. However, it is pretty ubiquitous at this point, so the best we can do is avoid PFAS in our lives and install treatment if it's an issue in your area. But I think it's also important to note that it's not just drinking water. So many consumer products and things we have in our homes and households also have PFAS in them. So it's a good thing to be aware of.
Thanks, Ruby. That's good to know. And it looks like we have another question. We do have about 2 more minutes left, so this might be our last one unless we get another quick one in. But Laura asks, are there any suggestions for education focused for middle or high school students? Any good resources out there?
I don't have any, but I would honestly be interested in talking some more about that. I think being able to communicate those kinds of things would be that'd be interesting to me and hopefully to the kids.
Yeah, ditto.
Gotcha.
And I see Laura just provided her email, so we can talk more about that. But last fall, I had the pleasure of talking with a group of middle school students from Delaware who were doing a research project on PFAS, which I thought was very advanced for middle school. And I had a Zoom conversation with them and answered some questions. So your friendly local EPA representative is always happy to be a guest speaker or talk to any students who are interested.
Yep, and same with Pennsylvania DEP as well. I would definitely direct you to look at our website, which is the that CEC website that I linked us to for surface water sampling. The high school students would probably get a lot out of looking at some of those maps.
The PFAS analytic tool website is also a fun map-based toolkit that students can use, and you don't need GIS to use it or anything fancy. You can just kind of play around and look for hotspots, look for point sources or discharges of PFAS. So
Ask and ye shall receive, Laura.
All right, great. Well, I'd like to thank Ruby, Charlie, and Amy again for the great presentation, and I'm going to pass it over to Maggie to close it out.